for each road type. And I underline these things. This distance zone 1, for example, 20 seconds. This distance zone 2, 3 seconds, like this. And this distance on-ramp is used for its on-ramp model. And I'm not going to talk about the on-ramp model. In today's lecture, I'm only focusing on this long segment, the lane movement, lane changing in the long segment. I'm not going to talk about the ramp or intersection. So, do you understand these concepts? If yes, let's go to another thing. Now we already know INSUP has 3 zones. And for mandatory lane changing, the logic will be very natural. So if you want to, in the second zone, you want to change your lanes because you want to make a turning. And the logic will be very obvious. So I'm only talking about the discretional lane changing, which is more complex. So in which situation do you want to change your lane? In the first zone. This is called overtaking. And I want to introduce these 2 parameters. INSUP's discretional lane changing is implemented using 2 parameters. The first parameter is called percent overtake. So the vehicle, I use V0 to stand for the current vehicle we are modeling. So the current vehicle will try to overtake another vehicle if the downstream vehicle is slower than this percent of its desired speed. For example, if the vehicle's desired speed is 100 kilometers per hour or 100 miles per hour, and the downstream vehicle is traveling less than 0.90 multiplied by 100, which is 90 kilometers per hour. So I want to travel at 100, and the downstream vehicle is traveling at 90 or less than 90. Then I will overtake it by switching to another lane. Understand this? So if the speed in front of me is less than 90% of my desired speed, I will change lane. So this is the motivation of overtaking or discretional lane changing. Another parameter is called percent recover. This means the vehicle will get back to the stall lane when the downstream vehicle is driving faster than this desired speed. So for example, I change the faster lane, and I find that the vehicle ahead of me is traveling faster than 95% of my desired speed. Then I will switch back. I will realize that this lane is too fast. I will go back. Understand? So we have 2 parameters, one for overtaking, the other one for recover. Overtaking means going to the faster lane, and and recover means going back to the slower lane. And for these 2 parameters, their influence will mainly be in zone 1 for the discretional lane changing. And it has some effects in zone 2, but in zone 3 it has no effect. Right? I want to give you another quiz because if I keep introducing it will be too boring. Let's consider this case. What will happen? If the percent overtake is equal to 90%, percent recover is 50%, then my current speed is 90, my desired speed is 100, and the current downstream vehicle speed is 88, and the lead vehicle in the fast lane speed is 100. What will happen? Imagine. In the beginning, let's use this overtake percentage. So my current speed is 90, my desired speed is 100, and this 88 kilometer speed is the downstream vehicle, and this is less than 90 multiplied by desired speed, right? So I want to travel at least 90 kilometers per hour, but the downstream is 88. So what will happen? I will change to fast lane. After I change to fast lane, the lead vehicle speed is 100, which of course is much better and much bigger than this recover. Then this ratio multiplied by desired. This multiplied by this will be equal to 250. Then I realize that I'm traveling too fast. Then I will go back. And this will result in an oscillation in the lane changing. So the vehicle will change to the fast lane and change back. And do you notice which is the problem? I mean, if you take a look at the default value, it will be 0.90 or 0.95. In my case, it's 0.90 and 0.50. So this makes the problem. So MSUM will recommend you to use large values of this percentage to recover. So this one should be larger than that one, and they should not be too small. Otherwise, the vehicle will change their lanes very frequently. That will cause the network traffic condition very unstable. Do you understand this? Yes. Now, in order to define these two parameters, you no longer have to go to the road types. You have to go to this experiment setting. So in MSUM, if you remember on the right, you have a lot of invisible elements. And there is one item called experiment. So for each experiment, you can specify this percent overtake and percent recovered. They are listed here. Okay. Now, I have already talked about the discretion or lane changing. Now I want to talk about the gap acceptance. The original gap acceptance model in MSUM, in the manual, was very tedious. It's very long, and I have shortened it, so it may be easier for you to understand. First, we define three vehicles: current vehicle V0, lead vehicle V1, lag vehicle V2. V0, V1, V2. First, understand this. Then the logic is like this. First, the adjacent gap has to be larger than the length of this vehicle, right? If it's even less than the vehicle length, then how can I make a movement, make a lane changing? So this is the first condition. The adjacent gap has to be larger than the vehicle length. Then you will calculate two speed. The first one is called down speed. This is the speed imposed by V1, the lead vehicle, and the lead gap to the current vehicle. What does this mean? This means if I change to the fast lane, then my vehicle will be subject to the car following model. And this will give me a new speed. Understand this? If I successfully change to the fast lane, then my vehicle and the lead vehicle will have a relationship caused by car following model. And this will give a new speed, travel speed for my vehicle. And this speed is imposed by the position of the lead vehicle, and our gaps. Our gap, right? Correct. Understand this? Down speed. So I change, then my vehicle will be restricted by the lead speed, the lead vehicle, and the lead gap. So this is first speed. Another speed is when I change, my vehicle will affect the lag vehicle also, because I am now I will then be the lead vehicle of the lag vehicle. So I interrupt their current relationship. I insert into the gap between them. So there are two speeds that have to be calculated. This is called up speed. And these two speeds, if they are acceptable, what do I mean by acceptable? So typically, when I insert myself into the gap, and then I probably have to slow down, and the lag vehicle probably also have to slow down, and these slowdown are restricted by the maximum deceleration. So in this sentence, if these speeds are acceptable according to the deceleration, maximum deceleration, then the gap can be accepted. Is that clear? Are you clear? Tell me. Do you already understand this? Do you want me to? Do you have any question? No? Okay. Okay, so in this case, we already talked about the discretion, the lane changing, and the gap acceptance. But you have some parameters to set. We have some cases called impedance lane changing. Now, it consists of two parameters. The first parameter is called percentage for impedance lane changing cases. This is the probability for one vehicle to change lane without a safe gap. So even the gap is not accepted, I may still change my lane. This is the first parameter we can set. By default, it's 0. So you always wait for a safe gap. But if you want want a vehicle to switch lane more easily, then you probably want to change it to about 0. The second parameter is called sensitivity for impedance lane changing cases. And this parameter, if it's bigger than 1, then the maximum deceleration of the lag vehicle will be overestimated. So this will also increase the chance of impedance lane changing. And they can be found here. So do you remember the first two parameters were set in row types. The second two parameters were set in experiment parameters. These two parameters were set in vehicle types. For different vehicle types, you can set these two parameters. By default, this is 0, which means safe gap only. This is 1, which means no overestimation of deceleration. Any questions? Good. So I finished AIMSA. Now let's talk about another one, VSIM. VSIM is different from AIMSA. Of course, they are quite